reactions of alkenes in this chapter, 9 of which are addition reactions. This is the second of the addition reactions called hydration of alkenes. In this reaction, we will be adding water to an alkene. Just as in the first reaction, we added HBr or HCl or HI. In this case, we're going to be adding water. But notice something different here. We also have something over the arrow, whereas with the HBr, HCl, and HI reactions, we did not. This is representing a catalyst. Notice that the product of the reaction is an alcohol. So what we're adding to the double bond, one of the hydrogens is going to add on one carbon. The remaining oxygen and hydrogen are going to add onto the other carbon. In other words, we're adding H to one and an OH to the other. And the net result is that we end up with no double bond, and the product is an alcohol. Notice it's a carbon group with an OH on it. We've learned that that's an alcohol. Now let's go back to the catalyst. Typically, chemists are going to write a catalyst, even if they're writing a balanced equation, which this is, they're going to write the catalyst over the arrow because it's not part of the balanced equation. It's there at the beginning and it's there at the end, so it cancels out. But it's important that it be there, so we put it over the arrow to represent its importance. Notice also that the catalyst in this case is represented as H+. I put that in quotation marks because the fact is, as you've heard me say, there's no such thing as H+. That's simply a symbol to stand for some acid. It could be sulfuric acid, it could possibly even be hydrochloric acid, phosphoric acid, or probably H3O+, since this is being done in water. Strong acids dissolve in water to produce H3O+ anyway, and so that's probably what the acid is. But this is just a generic indicator that there is some sort of an acid catalyst in the reaction. Now we learned with the hydrohalogenation reaction that the stereospecificity, in other words, which carbon gets which thing, matters, and that in that reaction it was called Markovnikov addition, meaning that the carbon that has the most hydrogens gets the new hydrogen. Well, it turns out hydration of the alkenes is also Markovnikov. The two reactions we'll see are very similar to each other. They are both Markovnikov in regiospecificity. Similarly, they are both nonspecific in stereospecificity. That means, if you remember, that some of the time the reaction adds the hydrogen and the OH both on the same face of the double bond, either the bottom or the top, and in some cases it adds the hydrogen on one face and the OH on the other face, either this way or this way. That's known as anti-addition. So we get some syn and we get some anti. That's called non-specific if you get both. Here are some examples. We're going to see what happens if we add water with an acid catalyst to 3-hexene, to cyclohexene, to 3-methyl-2-pentene, and 1,2-dimethylcyclopentene. Notice in each case it's the same reaction, although the reagent looks a little bit different. You have to get used to seeing all of these. In this case, I've put water over the arrow. I've put the catalyst, H2SO4, which is a perfectly fine strong acid catalyst, under the arrow. In this case, I've written H3O+, because that's what really happens when you put a strong acid into water. You get H3O+. In this case, I've written the water over the arrow as I did here, but I put the catalyst as H+, which is a more generic symbol, again meaning any strong acid. And in this case, I wrote the water as part of the balanced equation on the left-hand side of the arrow, and H+ as a catalyst over the arrow. So let's go ahead and see what happens in each of these 4 cases. In the first case, we're going to add a hydrogen to one of these 2 carbons and an OH to the other. And since it doesn't matter which one gets which thing, since the 2 ends of the double bond are the same as each other, notice the double bond is right in the middle of a symmetrical alkene. Markovnikov doesn't matter, so we could add the OH here, as we have done to get this product, or we could add the OH here and the hydrogen here, and that would also give us the same product, just drawn backwards. So in that case, it doesn't matter. What about in the case of cyclohexene? What will the hydration reaction give us? In that case, if we put the hydrogen here and the OH here, we will get cyclohexanol. Or again, like this one, since the 2 ends of the double bond are the same as each other, it's symmetrical, we'll end up with some where the OH goes here and the hydrogen goes here, and some where the hydrogen goes here and the OH goes here, but you get the same product in both cases. Now what about in this case? Let's consider that carefully. Notice that the 2 ends are not the same as each other. This one has a hydrogen on it. You don't see it there because this is one of those polygon figures, but there is a hydrogen at that position. You can draw it in if you want to. At this position, there are no hydrogens because there's a methyl group right here and an ethyl group right here. So Markovnikov says them that has gets. We'd expect the hydrogen, then the new hydrogen, to go on this carbon that has the most hydrogens, that is 1. and the OH go in this carbon that has the fewest hydrogens, that is none. Indeed, that's what happens. So notice what we've done is added a hydrogen on here, so this now becomes a CH2 instead of a CH. We've added the OH on here, so the methyl group is still there, but now it also has an OH. So we end up with a tertiary alcohol in that case. Notice in this case, the two ends of the double bond are the same as each other, so it doesn't matter whether we add the OH here or the OH here, but because this is on the ring and it has two methyl groups, it does matter the stereo specificity. So if we put the OH and the hydrogen both down, the two methyl groups would be forced to be both up, and we would get this particular product in which the two methyl groups are cis, and the OH and the methyl group on the other carbon are trans to each other. This would be called Syn addition because the OH and the hydrogen are both on the same face, in this case the bottom face, but they could also be both on the top, in which case we would get the enantiomer of it. Those are both Syn addition. In this product, notice that the OH on this carbon and the hydrogen on this carbon are opposite to each other. So the OH is up and the hydrogen is down. That forces the two methyl groups that were originally there, one to be up and one to be down. So this is anti-addition. The OH and the hydrogen added, one up and one down. The other way would be the OH adding down and the hydrogen adding up, and that would give us the enantiomer. So these two products are the Syn addition. These two products are the anti-addition, and we get both since, as we remember, this reaction is non-stereospecific. Now, what we want to do is consider the mechanism of alkene hydration. I would like you to keep in the back of your mind the mechanism of the hydrohalogenation reaction that we learned in the last video, and see how this reaction is similar and how it's different. In many ways, it's very similar, but right off the bat, you notice one way in which it's different. You remember the hydrohalogenation reaction was a two-step mechanism. This obviously is a three-step mechanism. So let's just do it step by step. In the first step, the H+, whatever it is, maybe it's sulfuric acid, maybe it's H3O+, but whatever the acid is, protonates, that's a word, P-R-O-T-O-N-A-T-E-S, protonates. Basically it means puts an H+ on. So the first step in the hydrohalogenation reaction that we learned before is in fact a protonation because the first step puts an H+ onto the double bond. Same thing is true for the alkene hydration reaction. Notice what we're going to do is attach the H+, and I'm choosing to put it onto this carbon over here. So there's the new hydrogen attached to the double bond. One of the two pairs of electrons from the double bond is now in here. It's moved in to form the bond between the carbon and the hydrogen. That leaves the other carbon without an electron, and therefore positive. So we get a carbocation. Think back to the hydrohalogenation reaction. The first step was that you put an H+ onto the double bond and formed a carbocation. In that case, we wanted to form the most stable carbocation we could, so tertiary was preferable over secondary, which is preferable over primary. The same is true here. So this first step, in fact, is exactly the same in this mechanism and in the hydrohalogenation mechanism that we saw in the previous video. So that's the first step. Just put on an H+. In the second step, then, we're going to attach that water onto wherever the positive charge was. In the hydrohalogenation reaction, you remember what we did in the second step was we added the Br- or the Cl- or I- onto wherever the H+ was. In this case, we're going to add the water onto wherever the H+ is, and so it becomes like this. And notice what we're doing is using one of the pairs of electrons on the oxygen to form a bond with the carbon, and that's this pair right here. Now the oxygen only has one pair of electrons. In other words, it's essentially given away one electron, and therefore it becomes positive. Or if you count the valence electrons here, you'll see that it has a +1 formal charge. So that's the second step, is the water simply attaches onto wherever the positive charge was. That's the second step. The third step, notice that we take this molecule we just had, and we have to get rid of one of these two hydrogens. So we remove it, it comes off, and becomes H+. What we have left is the alcohol. One of the hydrogens is gone. It's left this pair of electrons behind to satisfy the positive charge, but in the process it has itself become positive. So we end up with an H+ as a product of this third step. Notice that H+ went into the mechanism in the first step, came back out again in the last step. So it is truly a catalyst in that it's going into the mechanism in an early step, usually the first step, and then coming back out again in a later step, usually the last step. One thing you might notice that's of interest is this H+ that we put in to begin with the same hydrogen as this H+ that came off? Well, let's trace it through. The first H plus we put on becomes this one right here, stays attached to that carbon. In the second step, it's still attached to that carbon and it stays there. In the third step, it's still attached to that carbon and it stays there. Where did this H plus come from then? Well, it's one of the two that was originally on the water. So the water attaches here. One of these two H pluses then comes off and becomes that H plus. So this H plus that went in is not the same as this H plus that came back out again. But it doesn't matter because an H plus looks just exactly like an H plus and it doesn't matter where it came from. As far as we're concerned, it was there to begin with and it's there at the end. But like all catalysts, it actually becomes intimately involved in the mechanism, and it is important to illustrate in the mechanism what is the catalyst doing there anyway. Now let's do what we always do with mechanisms, and that is add up the steps. Notice that if we cancel out everything that appears on both sides, specifically the H plus obviously cancels, as all catalysts must. In this case, the carbocation cancels. The positive oxygen molecule, it looks like water attached onto a carbon, also appears at one point here and on the other side here, so it cancels out. And all we have left is the alkene. It's there in the balanced equation. The water, it's there in the balanced equation. And the final product, alcohol, it's there in the balanced equation. And again, I've written H plus over the arrow to indicate that there's a catalyst that you put in to begin with and you get back out again at the end. So this is a fine mechanism for the hydration of alkenes. So let's just compare again. How does this relate to the mechanism of hydrohalogenation that we learned in the previous mechanism or previous reaction? Well, it's pretty much exactly the same with the addition of a third step. So again, the first step is exactly the same. You put on an H plus onto the double bond and that forms a carbocation. The second step is pretty much the same. In the hydrohalogenation, we're adding a Br minus or a Cl minus, and so we end up with a product directly at that point. In this case, we add water, and we don't end up with a product directly. We end up with the product, but it has one extra hydrogen on it. So we have to get rid of that hydrogen and at the same time regenerate the H plus that we put on in the beginning. Now you might wonder, this is a critical thinking question, why couldn't we just start with the alkene and add the water directly? Why do we have to put in an H plus at all? Why couldn't the water just protonate the double bond to form the carbocation? That would leave OH minus as a product, and then the OH minus in the second step would attach to where the positive carbon was and would produce the alcohol directly. In other words, it would be exactly the same mechanism as the hydrohalogenation. One very easy answer. Why does water not donate an H plus to an alkene? Because it's not a very strong acid. It's not nearly a strong enough acid to protonate a double bond, whereas HBr, HCl, and HI are very strong acids. They are strong enough to protonate a double bond. So therefore, since the water itself isn't strong enough, we have to put in an external acid in order to protonate the double bond first, and then the water does its thing, which is adding on to the carbon, and then finally it loses an H plus in the third step. Now, what I want to do at this point, which we didn't do with the hydrohalogenation, although we could have, is look at each of the three steps in the mechanism individually and draw curved arrows and see how everything balances out. So, first step, we're going to protonate the double bond. So here comes the H plus, it's approaching the carbon-carbon double bond. One pair of electrons from the carbon-carbon double bond, indicated by this curved arrow, moves in to this position to form a new bond between the carbon and the hydrogen. That, of course, leaves this carbon without an electron that it had before, therefore positive. Now, I've written that first step again in a slightly different way, because, of course, as I've said, there's no such thing as H plus, really. The acid is probably actually H3O plus, which I've written here in a kind of a funny way. I've written it as H2O with a hydrogen attached to it, so it's really H3O and a positive charge on that oxygen. Well, that thing approaches the double bond, and one of the pairs of electrons from the double bond moves in to form a new bond with the carbon and the hydrogen, just exactly like it did here. This is really no different. But because this hydrogen was attached to the H3O plus to begin with, it has to lose this pair of electrons, which goes out and neutralizes its positive charge on the water and produces water as a byproduct in that case. So notice that this is exactly the same thing. This is just using a simplified version in which we're assuming the acid is H plus. This is showing what actually happens if the acid is H3O plus. If you consider the acid, on the other hand, to be HCl, then this would be chlorine, and it would leave as Cl minus. Or if this was sulfuric acid, then it would leave as HSO4 minus. But whatever the conjugate base of this acid is, that would be produced in this case. All of those are again represented in a simplified form by just putting in an H plus at that point. Here's the second step in the mechanism. So what happens in the second step? The water approaches, and it's going to share a pair of its electrons with the positive carbon. So we're going to draw a curved arrow here to show that this pair of electrons is now coming in here to form a bond with that positive carbon. So now this is that single bond. But by doing that, the oxygen now has 3 bonds to it and 5 electrons instead of 6, therefore it has a positive charge. Or we can think of it as having donated, essentially given away 1 electron. So instead of being neutral as it was here with 6 electrons, it now has a positive 1 charge because it only has 5 electrons. Again, the curved arrow is useful in showing how that bond gets formed. The third step in the mechanism shows how we lose the H plus off, because remember the third step is just dropping off an H plus. So this pair of electrons, or you could show this pair equally well since they're essentially the same as each other, but one of the pairs that's holding a hydrogen onto the oxygen is drawn into the oxygen, because the oxygen being positive, it really wants to get electrons towards itself, so it pulls this pair onto itself and it becomes a lone pair, and at the same time it drops off the H plus, which notice that again there really is no such thing as H plus, but this would probably be picked up by water, in which case water would be donating a pair of electrons into the hydrogen and forming H3O plus, or this might be a Cl minus that's picking up the H plus and becoming HCl, or it might be HSO4 minus that's picking up the H plus and reforming H2SO4, or whatever the acid is. Again, the H plus is just representing some acid that a conjugate base will have reacted with this H plus and produced an acid on this side. That's the end of this video. Thank you very much.